Today's topic is going to be cryptography, and it's my understanding that you covered some aspects of cryptography already, and that's great. But I'm going to be taking a more general view of cryptography and talking about cryptography over the period of pretty much our entire history, because while we often think of cryptography as being something that's computational and that we pretty much only use computers for, it is something that's been around for a very, very long time. And the forms that it has taken have changed and evolved, and we can look at as far back as the ancient Egyptians using hieroglyphs and different sorts of encodings for their information to either hide or to make it more difficult for others to understand. And one distinguishment that I want to make between cryptography, sort of encryption, and codes. So it's often times that information is put into a code. So for example, you may have heard of Morse code, a series of dots and dashes that represent letters, and you put those together to make words and things. And these are different than sort of encryption schemes because everybody can know that code. So for example, Morse code is known by everybody. You can look up how to to break that code. And that's one of the big distinguishments, because with encryption, you have something called a key, which is some sort of unique value or identifier that allows you to take some text and make it unreadable, and then take that unreadable text and make it understandable again. So, sort of the more familiar type of cryptography is what I would call modern cryptography. And there are several key aspects that are somewhat unique and important to this area, namely confidentiality, integrity, authentication, and non-repudiation. Essentially what these are, I'll go through each one. Confidentiality, pretty self-explanatory. The information that I send or store stays confidential, so nobody can know what I'm sending or what I have encrypted unless they're meant to know. Data integrity, so if I'm sending data over like the internet or something like that, or if I'm storing data for a long period of time, then the encryption scheme or the cryptographic scheme, it ensures that the data, if it changes somehow, if there's like an error in the transmission or an error with the hardware that causes some information to be destroyed or corrupted, then that can be detected. Authentication is essentially that whenever I'm sending data, the recipient can know that I'm the one that sent it. And non-repudiation is where if I send data to you, then I can't later go back and say that that wasn't me that said it, and that's not what I said. Now, of course, there are some sort of exceptions to this, but that is sort of the goal of modern cryptographic schemes, is to hold all of these things true or maintain all of these things. So some terminology to cover just before we get into like the actual implementations of some of these schemes for cryptography: adversary, plain text, ciphertext. So plain text is essentially any message, data, or anything that you want to hide. So this is something you can understand or you can use. So for example, plain text is often referred, one example of plain text would be just text, just regular, a message that you want to encrypt and hide. Now, once you put this text or information through an encryption algorithm, which is to say that it's converted and hidden from the, anyone who wants to look at it, then that would be called the ciphertext after it's gone through that conversion process. So this ciphertext is not human readable. It's either jumbled or shifted or transformed in some way to make it so that it's not clear what is actually represented in that information. Now, an adversary is someone who's trying to figure out what is in that hidden information, that hidden ciphertext. The adversary wants to break into that and figure out how it was created so that it can reverse it and get the real message. And this is, has a lot of implications in many areas of our daily life. For example, transactions and, with like credit cards and things like that. So keeping your information secure, logging into social media, all of these kinds of things, like, online banking, everything, all of this kind of modern, modern things that we take advantage of or take for granted, they're made possible by cryptography. So to sort of define encryption, since you guys have already been exposed a little bit to cryptography, I'm just going to kind of, blitz through this, but essentially encryption is taking some plain text and going to, some hidden information, some ciphertext, and decryption is, taking some transformed information that you can't really understand and converting it back into the plain text. And the way this is possible is by using a key. And this is, again, unique to the scheme or the instance that you're using it. And this is what prevents just anybody from being able to, access the information. So let's move on to why should you care about cryptography? Well, I kind of briefly mentioned, its implications with, like e-commerce and like credit card transactions and things. But, this sort of stuff is sort of transient, maybe. Some closer examples are with things like social media and your personal accounts and, emails that you communicate with your friends or text messages that you send to your friends over messaging apps. These are all kinds of things that we do take for granted in that they are secure and that we know that what we send is going to be received, and we even know when it's received. And so it's sort of tough to imagine a world where, none of that is possible. And in fact, it would be pretty crazy, if you could send messages and not have any guarantee that, somebody was receiving them or that maybe they had been transformed in transit. And so what your desired recipient actually receives is very different than what you intended. And this, has huge effects on, national and global scales as well. So with all aspects of cryptography, maybe you want to protect some national interests and national security by keeping information out of the hands of, nefarious parties that want to, that don't have the best interests of your company or nation at heart. And so that's one of the biggest use cases for cryptography and computer security as a whole. So let's move on to how to actually use cryptography, right? So this is kind of the more hands-on, the more example-driven stuff. Before we actually get into the ciphers, though, I do want to mention that one aspect of cryptography that's sort of underrepresented and underemphasized is the importance of strong passwords, for example. So, with data authentication, when you sign into a social network or something, or when you log into your computer, the thing that you are, when you're authenticating yourself with that password, that's cryptography as well. And so that's one of the reasons why a lot of emphasis is put on ensuring that you have strong passwords. And this is one of the worst areas of cryptography because it's so vulnerable, or it's so common for people to choose poor passwords, and that makes that really weakens the security of a lot of businesses and and individuals as well. So now we'll talk about classical cryptography. And when I say classical cryptography, I'm really talking about pre-computational, pre-computer, or digital computer technologies. And these sort of schemes are often lexicographic, meaning that they are shifts in characters or reordering of characters or some other transformation. The first of these that we'll be discussing is called the transposition cipher. And with a transposition cipher, what you're doing is you're reordering the letters in a message according to some key. So in this example, we've got the message, hello QCamp. And the key that we're using is QCat. So in this example, we're taking the message, we're filling a grid with that message, and then reordering the columns according to basically the ordering of the key. And then reading off the rows of the reordered columns to determine what the final encrypted message is. And one thing I want to focus on during this is actually looking at the output of some of these and trying to determine what it actually is. So with this example, you can see down here that this message, the cipher text, it has several capital letters. It has a random dash, in there, and the space is somewhat, skewed and different in a weird location. So this sort of arrangement of the characters would give the impression that this is a transposition cipher, because you see a lot of uppercase, lowercase, no numerical values, and you can think that, okay, if we keep the punctuation the same in the message and we're reordering that, it would be hard to imagine a word that has a dash like this and that has like 2 letters after it, or a word that has a final letter that's capitalized. And so that would kind of give you the impression, or it should give you the impression, that that is a transposition ciphertext. And then, I've gone through sort of the steps here written out, but, to sort of mention here, as mentioned here at the end, this isn't the only implementation of a transposition cipher. There are several other, examples of how to perform this kind of cipher. Differences in the way that the key letters are arranged, or how that the columns are manipulated, or the way that the columns and rows are read. These are all just different types of approaches to the same, same general area. Next, I will be talking about Caesar ciphers. Actually, before we jump to Caesar ciphers, I want to show you some of the relevant things. So as I mentioned with strong passwords, this resource that you'll be getting with your the cryptography scavenger hunt materials later, it shows you the top 200 most common passwords. And so, if your password, for example, was in this list, you probably wouldn't want to continue to use it. because it's very vulnerable to an attacker or an adversary, to use the words of the notes. And another example of this is an online tool that allows you to do transposition ciphers. So if I type a message here like hello, this is a message, and then I have the key here as key, and I click on encode. Well, then I get this jumbled message down here. And again, we can see that there's 2 space characters in a row right here. And these spacings and arrangements would give you sort of the idea that this may be a transposition cipher. And of course, if you wanted to decode a message like this, then you could just take the ciphertext, put it in here, give it the same key, and just tell it to decode, and it would be able to essentially undo the encryption or perform decryption. This is an example of transposition cipher. And you can see how it works by looking at the grid here and seeing that, yes, it uses a slightly different approach, but in the end, it's very similar, and it's just a slight tweak on the actual approach. So then the next cipher that I want to look at is the Caesar cipher. Now, Caesar ciphers are pretty simple in that the way they work is you take a message and you take a letter and you just shift it by a set number. So for example, if I'm shifting A by, I think I use the example of 6 here. Yeah, if I shift A 6 positions, then I get G. And so then the mapping I would get is A to G, B to H, and so on. And so you're essentially shifting the alphabet by 6 characters and looping it around to from the end. So if I'm shifting the alphabet to the left or backwards, then Z would be matched. You can see over here that Z would be matched with T, for example, in this, and so on. And so it just wraps around, kind of like a loop. And if you were to be doing this, the scavenger hunt later in person, one of the best tools for trying to do a Caesar cipher or even a substitution cipher is called a one of the reasons why the Caesar cipher is also referred to as a wheel cipher is because you can take 2 wheels of different sizes and cut these out, label the different letters or characters, and sort of rotate the inner wheel to sort of get the mappings for different shifts. And that can make it really easy to find these kinds of, to break these ciphers. And again, I'll show you one of the tools that you'll be using later. This is an example of something we'll talk about in a minute for frequency analysis. But you can see here that you can shift you see Caesar cipher here, and you can shift the letters in the word until you get a match. And since there's only 26 letters in the alphabet, it's quite easy to just cycle through all of the options if you think it might be shifted text. So the last classical cryptographic algorithm I'm going to be talking about is substitution cipher. And it's very similar to Caesar ciphers in that you're still substituting characters in the alphabet for another character, but there is no guaranteed shift. There's just a mapping between essentially one letter to a random other letter in the alphabet. And this makes it much harder to decrypt. However, one of the biggest weaknesses of the substitution cipher is frequency analysis, which is where we look at the frequency of letters that we're seeing in the word. So let's say, for example, we know that E is the most common letter in the English alphabet. In the English language, it's the most commonly used letter. So if the message that we're looking at, if it has a frequency where we would suspect that the highest frequency letter that we're observing would match with E. So in this case, R has the highest frequency of any letter in this message. So we can conclude that E probably goes along with R. That is sort of a reasonable assumption that you can make. Some other things that you want to keep an eye out for are repeated letters and things that can kind of give away words. For example, if you see in the middle of a sentence a letter on its own that is capitalized, it's probably the letter I. Or if you see a letter in the middle of a sentence that's a single letter with spaces on both sides, it's probably the letter A. You know, these kinds of things that you can look out for and use to conclude what a letter might be. And you can, again, to sort of recognize whether something might be a substitution or a Caesar cipher or not. I mean, this text is decoded now, but let's shift it a bit. So, you know, with this, you can see that, you know, the first letter of a word is capitalized. The punctuations are in the correct locations they're in reasonable locations for a word. And so this kind of format would give you an idea that it probably is either a Caesar cipher or a substitution cipher. So that's sort of the area of classical cryptography in a nutshell. So, oh, and also, if you have any questions, feel free to you know, speak up or to message in the chat, and I will answer your question. So, you know, just feel free to do that at any time, and if I catch it, I'll answer it. So to move on to modern cryptography. So as I mentioned before, and as we've seen with these examples, with classical cryptography, most of the transformations and the substitutions that we're doing are lexicographic, meaning that I'm just substituting, shifting, or transforming the letters into, you know, sets of letters or, you know, just one other letter. And that's fine for the past, where this was all being done by hand, and, you know, you had to make it hard enough to break, but also easy enough to decode by hand. However, with, you know, modern day computers, we can, you know, manipulate information and everything and data mathematically. And so we can use mathematics, statistics, and information theory to make much more secure algorithms and approaches to encrypting data. So before we get into the actual schemes that I'm going to touch on, I wanted to mention several data types or data formats. So if you're familiar with computer science at all, or if you've had any exposure to it, this will probably be pretty familiar. If not, however, that's no problem. I'm going to go through each one. So on the top here in this table, the first element we see is ASCII text. And this is just a, you know, this is just a name for one way to represent text in a computer is ASCII. And so we have the message hi. Now, if we go to the next row, we have binary, which we would call base 2. And this is actually how you would represent each of these letters in binary. So, you know, this set of 8 digits, this byte is also called, represents the letter H. And this byte represents the letter I. Similarly, if we were to take these binary numbers and convert them to decimal, which is essentially our normal number scheme that we use when we count to 10 and beyond, this is essentially the decimal representation of these letters and this binary string. Another sort of less common way, practically speaking, for non-computer science terms, you probably have not been exposed to something called hexadecimal, which is base 16. And essentially you're still using, you're still counting, but instead of counting, 1 to 10, you can count, 0 to F. So you go to 9, and then A, B, C, D, E, F, and then you go back. So this is sort of, this may be very new to some of you, but essentially what you're looking for with a data type like this is if you see numbers from 0 to 9 and letters from A to F, and that's all you're seeing, it's probably hexadecimal. Lastly, one other common way to represent data is with base 64. And it's a similar approach to hexadecimal, but to get 64 different characters, we have to tap into lowercase letters, uppercase letters, different symbol characters, and so on. And so when you're looking at something that might be base 64, it's going to look very jumbled. And we can take a look at this a little bit in a little bit more detail. This is one of the more powerful tools that you'll be using for the scavenger hunt later on. Oh, sorry. And this is a tool called CyberChef. Now, if we go down to the data formats, we can see over here that we've got from hexadecimal or to hexadecimal. So if I type a message over here and I just say, here is my message. Okay, so let's say that I want to convert this and see what it looks like in hexadecimal. Well, I can see here that, I've got D, for example, here, and another D here. And, I'm not really seeing anything beyond, E and F in characters. And so this would tell me that this is, essentially hexadecimal. Now, let's see if we can find the base 64 option. And we can take this again to base 64. And so you'll see in here that there are capital letters, lowercase letters, numbers, and even some, maybe some different characters like, equal signs and commas and things. So that again is a very strong indication that you're looking at base 64 text. And notice here that I have put both a hexadecimal and a base 64 filter on this text. So I've converted it twice. And that's one common way to essentially hide data or obscure data a little bit. It's not truly encryption, but it's just one way to sort of hide the data a little bit better because it's not human readable. And so you've got to kind of play around with it. And that's essentially what you need to know about these different data formats before we continue. Now, the first type of modern cryptographic scheme that I want to talk about is symmetric encryption. The way symmetric encryption works is that you take the plain text, you use a key to encrypt it, and then you use that same key to perform decryption. And this sounds pretty familiar because all the schemes that we've talked about so far are this way. If you're doing a Caesar cipher and you have a specific shift that you're doing in all the letters, that's essentially your key. So you shift all the letters by some amount, and then to decrypt it, you're just shifting it by that same key, just in the opposite direction. And if you're decrypting, know that you're just performing a different operation, but with that same key. And sort of the most common approach to performing symmetric encryption is AES. And it stands for the advanced encryption scheme. And down here is where I mentioned that. And specifically, the most common implementation of AES is 256. And this -256 essentially indicates the bit length or the length of the key that's being used. And you can think of a key having a length as in with the Caesar cipher, the key length is very short. It's just a single number shift, and that's all you need to know. With a substitution cipher, the key is essentially 26 letters because you need to know the mapping. And so you need to know every single letter to be able to perfectly decode the message. And this is essentially a much longer key. We've got 26 characters. And to try and brute force and solve that for that key, you'd have to essentially cycle through all the possible letters for each letter of the alphabet and the arrangement. And so you wind up getting like 26 factorial or 25 factorial different combinations of passwords that you could have, or keys that you could have for an asymmetric algorithm like the substitution cipher that only has a 26 character long key. But with AES, with a key that has 256 bits of length, you gain a lot of security because you have to essentially, you get 2 to the power of 256 different combinations, and that makes it nearly impossible to brute force and solve by just testing every possible key. Another thing about AES is that it's quite secure. So even computationally speaking, you essentially have to brute force it to solve the, to break the encryption. The downside to a symmetric encryption algorithm is that if I'm trying to communicate with you and I encrypt my message, I assume that you already have the key. But if I have to send you the key and someone intercepts it, an adversary intercepts the key while I'm sending it to you, then any message that I encrypt with that original key and send to you, well, if the adversary intercepts it and they've already got the key, they can decrypt it, and everything I'm sending is basically insecure. And this is one of the things that quantum key distribution is important for, because if we had essentially perfect key sending, and there was we could always tell if the message that was sent was tampered with or that it was viewed somehow, like you can with quantum key distribution, then we would essentially be able to know whenever our key was sent had some kind of manipulation or interception, and we could send another one. We would know not to use that one. And so that would allow for essentially very secure encryption and communication using symmetric schemes. So I will be moving on now to asymmetric encryption. And the biggest difference here is that you have a key that you use to encrypt the message, and then you take that ciphertext and you use a different key to decrypt it. Now, the key that you use to encrypt a message is something that you make public knowledge, and so everybody can access or see that that public key, and so they can encrypt any message that they want. but the decryption key, you keep that private so that nobody else can see it. So then whenever someone encrypts something and sends it to you, you're the only one that can decrypt that message. And asymmetric encryption schemes rely on something called a one-way function. Essentially, what one-way functions are these processes in which it's very easy to go in one direction, but very hard to solve for the reverse. One common example of this is prime factorization. So if I take two prime numbers, let's say that I've got two very, very large prime numbers, and I multiply them, which is an easy operation to do. I just take two numbers and multiply them, and I get one very large number, right? Well, if I try to solve for the primes of that number without knowing what the primes actually are that give me that number, it's quite difficult to solve for that. So for example, if I have P times Q, and that gives me N, and I'm only given N, and I have to find P and Q, that's a very hard problem to solve. And essentially you have to try, every combination of prime numbers that might give you that. And that is a very difficult problem to do. And that's where the security comes from, is that it's hard to break these algorithms. However, if there are advances in computational algorithms to solve these problems, let's say, for example, that I come up with an algorithm that can solve, for primes in a very low amount of time. Let's say like exponentially faster than the current approach, which is trying every possible prime number. Well, that would essentially make the security of something like that uses prime number factorization as a security measure exponentially weaker. And I chose to discuss prime factorization here because the most commonly used asymmetric encryption algorithm is RSA, which you have discussed before. Now, the most common use for RSA is for communication and to actually exchange symmetric keys. So as I mentioned before, with symmetric encryption algorithms, when you're sending messages, you have to first send the key, and that communication channel, that communication method is insecure because you essentially have to send that key non-securely. So with asymmetric encryption, though, I can encrypt my symmetric key, send the symmetric key to someone who has a private key, and they can then decrypt it, have the key, and we can communicate securely from then on. And that is one of the primary uses for asymmetric encryption, because it's much slower to actually perform the encryption and decryption, and in general, it's just inefficient. One other example of encryption that I want to talk about is one-time pad. Up to this point, I've been talking about computationally secure encryption schemes. And what this means is that I've assumed that the adversary that that may intercept my messages, I've assumed that they have some limitation in the amount of computational power that they have, whether that be financial, technological, or physical. Like it might just be that there was a physical limitation and a technological limitation on the amount of computational power that they have. And if I then assume instead that they have unlimited computational power, in practice this would never really happen, but it's just a way of looking at the problem. So if I do assume that, if I assume that they have infinite computational power, then all of the previous algorithms would be essentially broken. You could solve for all of the keys and everything. But with one-time pad, it is something called information theoretic secure, which means that if I have a random string of numbers or letters or something, I have a random string of information that I'm using as the key. And the person that I'm sending a message to, if they already have that same random key, and I send the message with that key to them, then that correspondence is completely secure. Some of the caveats of one-time pad is that that random key that we both have, it has to be only used once. That's where the one in one-time pad comes from. And so you essentially have to discard that key after you use it one time to ensure that it stays secure. And one of the methods that people used to actually, effectively do this approach is that they would actually have a pad of paper, like a notepad, with a series of different keys in the notepad. And so you would have two of these identical notepads, and you would meet someone in person, hand them the notepad, and after you would each use one of the keys, you would burn it so that it would never be used again. And that is where the pad in one-time pad comes from. And the way that one-time pad is actually implemented is that you're performing performing modular addition and modular subtraction when you're decrypting. If you're not familiar with modular operations, essentially what modular means is that it's just the remainder. So if I had, for example, like 2 mod 4, right? 2 mod 4 would just give me 2 because 4 doesn't go evenly into 2. And the remainder of that division would be 2. That's how you can kind of think of it. So with the first letter here, if I'm representing A as 0 and Z as 25, then if I'm using the key here specified as ZAMVO, and I'm trying to send the message hello, then I would add the numerical values of these letters. So in the case of the first one, it'd be H and Z. So I'd have 25 plus 7 would be 32. Mod 26 is just 6, and that corresponds to G. So then I would send this GEXGC to the other person. They would use that same one-time pad key to perform the decryption using subtraction, modular subtraction, and you wind up getting the same message. And there's a lot of restrictions with this, but it is perfectly secure. And that's one of the reasons why I think it's important to touch on it here. The last thing that I want to sort of talk about and address is steganography. So up to this point, again, we've been talking about ways to take the message that we want to send to somebody, transform it into something that is indistinguishable, and then send it, assuming that they can't break it or that we're sending it perfectly securely. However, maybe we want to send something or store something in a way that they don't even know that we're sending a message. So one example of this is in history, for example, is a depiction of Herodotus in Greece, tattooing a message onto the head of a slave and then letting the hair regrow to hide the message. So then you send this person off to someone else, and they would just shave the guy to then get the message. And no one would know that there's a message there because it just looks like a normal a normal guy. And if he was caught, unless they knew about the message, there would be no way to know it was even there. And so that's sort of the approach that steganography is trying to mimic or trying to take the form of. And in modern terms, this can be accomplished with a couple different ways. So one way is to perform like color filtering on an image to highlight certain aspects and then extract that. In this example, it's very clear that there might be some information there even without the filters. But let's say that I have a document, right, a PDF document, and somewhat randomly throughout, I have put some small specks on the document that encode a secret message. And you can only see them under a certain filter, and they're so small that they almost look like printer marks that from like scanning the document into the computer. And this kind of approach allows you to hide information very, essentially in plain sight. Some other more modern examples are something called least significant bit steganography. What you can do is take an image, for example, and you can take every image has RGB values, red, green, blue. So you can take the binary representation of each of these colors for a given pixel, and you can take the last couple of bits of the information and replace it with information to hide either a message, or if your image is large enough, you can even hide other images inside of another image. And I'll show you an example of this here in a moment when I go through some more of the tools that you'll be using later on. But here you can see that they've taken the last two bits of this and essentially hidden the letter S for SOS. And effectively, this doesn't change the color because the last two bits of the image or of that pixel, it doesn't actually affect the color that much. The most significant part is, the farther over to the left bits. Those would be called like the most significant bits. To see an example of this sort of in action, you can look at these two images, and the image on the left is the original image, and the image on the right is an image that has some text encoded in it with steganography methods like this one, like the least significant bit approach. And there's essentially no way with the human eye to distinguish which one of these has a message in it. So let's say that I want to send a hidden message to my friend. I can encode a hidden message in an image and then send that to him, and he could then know that that's something I would do and try to decode it and see what I may have said. And this is really interesting because you can pretty much hide anything given that the host image is large enough. And you can do the same thing with video, audio, pretty much whatever you want to use as a host image you could theoretically use. Now, I want to go through an example of a tool like this. So this sort of online tool that I found for the purposes of our scavenger hunt later is pretty effective. So let's say that I pull up this image of bamboo, right? And I import that. Now I want to hide the message, this is a hidden message. And so I go ahead and I submit that. And so now what it's going to do is it's going to go through the pixels of that image, modify the last 1 or 2 bits of every pixel value until it's hidden my entire message. Now then, what I can do is go to the decryption part of the same tool, and I can import what they've labeled here as a steganography image, but you could essentially, rename this to something very harmless and send it off and no one would know. And then I can save this to my computer, the output. Now, if there's nothing there, this tool will tell you that there's nothing there, assuming that you use this same tool to encode it. Now, if I go to my downloads and I look at the output here, I can see that I can extract the message. This is a hidden message. And that is one of the really cool things about this, is that this is something you could effectively do yourself for fun and with your friends or whatever. And you'll be needing to use this for the scavenger hunt here in a bit. So some more things I guess I can talk a little bit more about this tool for a second, and these tools in general that you'll be looking at here in a moment. There was a couple options on the decryption side where you can view the text of view the hidden text in the browser. You can determine what kind of file is hidden in that image or audio file. And you can also just download that file. When you download the file, it will be saved as a text file. As you saw, it was out.txt. However, let's say that I hid an image inside of another image. The output file would still say out.txt, and I would just need to change that file extension to, like, for example, JPEG, JPG. And you can just do this in, if you're on Mac, you can just change it by, renaming the file. If you're on Windows, you have to enable under the view to actually see the, extensions, and then you can modify them the same way, and you actually see the change happen in the file. And beyond that, if you ever get stuck on, say you receive an image and you want to know what kind of file has been hidden in this image, you can have it guess the payload. And what it'll do is it'll look at any possible data that's been hidden in the file, and it'll construct it, and it'll look and see, okay, is this an image? Is it an audio file? Is it, what is it? Is it just text? And then you can use that to kind of guide your renaming of the file to the correct extension. So that generally covers all the tools that you'll be needing for the scavenger hunt and the general material that the scavenger hunt covers. If you have any questions, though, I am happy to answer them. So feel free to message me in the chat, or say your name and just ask a question. Because for the most part, I've covered all the material that I want to cover